This next demo I'm going to show is examining what's called the IRR estimator. So if you haven't watched the prior video on the WDD, which I go over a little bit more of the details here. So the WDD estimator is essentially, it assumes crime is distributed according to the Poisson distribution. And this next estimator I'm going to show also makes that same assumption, the incident rate ratio. But it's basically, instead of estimating a cumulative crime reduction like 10 to 7 in that prior video, this is estimating, it's more like a percentage reduction. So here in this scenario, we have our still same baseline, 10 crimes. And instead of going down as our target for 7 crimes per month, our target here is a reduction, an incident rate ratio of 0.7. You can basically consider this pretty similar to like a percentage point reduction. And so this is essentially saying if the target is 0.8, that would be like a 20% reduction. If it's 0.7, it's like a 30% reduction, so on and so forth. And so it works pretty similar to the prior scenario here, but instead of being a cumulative reduction over time, like I showed in the prior WD graph, it's more similar to that. It's that consistent per unit time over time. And so we basically have this estimate of that IRR is 0.7, and then over time, when you're monitoring those crime counts, our standard error around that estimate reduces down over time. I have additional documentation about when I think you should use the WDD estimate versus when you should use this IRR estimate. Like I said, sometimes people find this easier because it's based on like percentages. So it's an approximately 30% reduction in this scenario. But one of the main benefits of using the IRR is when you have very different baseline crime counts in the treated and control unit area. So say we have 2 years of pre data. And in this scenario, if you don't have any prior time periods, you really still need like that same consistent control and treated count. But what is different between this and the WDD tests is that here in this scenario, it's okay to use different baseline counts of crime. Basically here, what's called the identifying assumption of this particular estimator, when I talked about in the prior video that the treated and controls area should trend up and down approximately the same over time. It's that same trending up and down should be approximately the same here in your control and treated units, but it should, that trending up and down, if you plot it on a log graph here and they're approximately parallel, that's what you want in this particular scenario. So if you take log base 10, this would be approximately 1 and this would be approximately 2. And so if you can plot those logs, crime counts per month over time, and you can see like the treated area is typically around 1 and is flat, and the control area is around 2 and flat, or they basically parallel each other up over time, but they're those that same on the log graph, it would make more sense to use this IRR estimate. And so you can go hit calculate and plot after you've updated those estimates. And so you can see here that in this particular scenario, we only end up needing to monitor this particular crime event for 4 months before our estimate doesn't cover 0. Now, this is basically like a best case or a guess about what you think is technically possible with your particular intervention. Sometimes when you're planning out, you want to be conservative. So you want to be like, oh, maybe I can only think I can reduce it down 10%. Let's see. In that particular scenario, it basically, we would need to do this intervention out more than 2 years. And you can essentially have more post time periods if you want. So let's go out to 4 years, just as a hypothetical to show it, to see. And in this scenario, it's still, our estimator still doesn't even, it still never gets small enough to not cover our baseline estimate of 1 over time. So basically, if this is our treated units and this is our target, basically we're not going to be able to, in years and years, know if we can reduce crime. But if we think that we can either reduce crime more, we'll be able to have a better, basically have a smaller standard error estimate to know that it doesn't cover 0 in a shorter time period. Or we should try to think about potentially expanding our treatment area. So say you can change this baseline up to more crimes. And here you can see it still takes a while. It still takes almost 2 years to basically not cover 0 in this particular scenario. But if we can basically expand the treatment to more areas, or have more prior time periods, or more control units, or a greater expanse of control units that still meet that parallel trends assumption, basically our standard error will get smaller and smaller over time. Note though that the standard error, having this control units go up and up and up, there's basically, you're kind of bounded based on this smaller area. So you don't really gain anything by, say, having the rest of the United States as the control unit. You basically, this treated area, how many counts of crime are sort of in that baseline, sort of like limit how big that standard error can be. And there's basically, at a certain extent, it can never get smaller based on these treated number of crimes. So really, for some experiments, especially with rare baseline counts of crime, it may just not be feasible to, in any realistic time period, know if your intervention is working.